The short journey between history, math and instruments starts with a quite philosophical question. Does the exponential really exist? It should, since it is widely used in many aspects of our life, for growth or decay models, in biology and physics for instance, as we unfortunately know. The exponential is so important that the XP function key on calculator allows us to compute it or to draw its graphical representation with a certain accuracy. Do you need higher precision? Use a computer. But does it really mean that the exponential exists? From a certain perspective, the construction of a graphical or a curve by computation is significantly different from tracing circles by a pair of compasses. Compasses play the geometric definition of a circle as the set of points at a constant distance of a given point. We could say that the compass directly embodies the definition of the circle. We can now rephrase our initial question. Is it possible to find a tangible construction for the exponential in a material way as done for circles by compasses?
Besides the compass, we can think of many methods to trace geometric curves, such as the Gardner ellipse. Their richness is that they can connect the behavior of material tools to certain mathematical properties that define the geometrical object. For example, a taut string can keep constant the sum of the distances from two fixed points. By linkages, strings, and linear slides, we can construct a larger family of curves called algebraic. So we are in debt with Descartes for that. However, none of these methods look useful for our exponential. Indeed, the exponential curve is not algebraic. In the later Leibniz nomenclature, it is transcendental because it transcends the polynomial limits imposed by Descartes. To construct the exponential, new ideas were needed. The solution came through an outsider of mathematics, Claude Perrault. He was an architect renowned for his contribution to the design of the Louvre. In the sparkling Parisian 1670s, he proposed the problem of identifying a specific curve constructed in a very simple way. After putting his pocket watch on the table, as represented in this image, he dragged an extremity of the chain of his watch along an edge of the table. In this construction, the friction of the watch on the table is crucial. It makes the chain taut and always tangent to the curve to be traced. The ancient tangent problem to construct a curve tangent to another one is inverted. Constructions like Perrault's allow to draw also new curves starting from their tangent properties. That marked the beginning of a new method for geometrical constructions, the tractional motion, and Perrault's curve was named tractrice. Given such a curve, scholars like Huygens and Leibniz were able to construct, by straight edge and compass, the quadrature of the hyperbola. In a modern term, they could build the points of the logarithmic curve, or equivalently of the exponential one, from the trace of a tractrice. However, construction by dragging a load are not so accurate. To find instruments able to trace precisely curves by the inverse tangent problem, we have to wait for the beginning of the 18th century. Instead of the dragged weight, there was a wheel guiding the direction of the curve to be traced, exactly as one decides the trajectory of a bike by the front wheel steering. Such a technical improvement was introduced for the first time by an almost unknown English teacher, John Perks. But the first efficient and professional machines were designed a few years later by the Italian professor Giovanni Poleni. He not only designed the machines for the exponential and the tractrice, but constructed them for the University of Padoue. According to the most recent catalogue of the Museum of History of Physics of Padoue, we seem to be lucky. These instruments are still in there. Hence, let's go there to see them in action.
So great to be in Veneto. Veneziani gran signori, padovani gran dottori, vicentini mangiagatti, veronesi tutti matti. Besides the atypical receipts of Vicenza and the craziness of the city of Romeo and Juliet, we are interested in the first two cities. Indeed, besides the glories of the capital Venice, the University of Padua was founded in 1222. Thus, it is one of the oldest surviving universities in the world. I'm so honored to be here. Hello, Sofia Talas. Thank you so much for your availability, and it's an honor to meet you again. And we have a question. We are looking for some machines tracing geometrical curves. Are we in the right place?
I hope so. But first of all, welcome to the new Giovanni Poleni Museum. We actually inaugurated a few days ago. Well, we actually have such a machine in the museum's collection. Shall we have a look at it?
Okay, some pulleys, here a sliding part, okay, another string that comes here, maybe connected to the pulleys in this one, a tracer, okay, but honestly I'm not understanding how it works and how that could trace a logarithmic, a tractrice or something like this. Any idea?
Well, maybe we could have a look at Poleni's original paper. Poleni described his machine to draw tractrice and logarithmic curves in a letter to Jacob Hermann. The letter was published in 1729, and it was actually quite a success at the time. Euler was very interested in it, for instance, and he got in touch with Poleni. They stayed in touch for several years discussing about those kind of problems.
I recognize that. It's Perrault's construction of the tractrice with the clock. Okay, and here is the one for the tractrice. And here is the machine for the logarithmic or exponential curve. But wait a minute, such a machine doesn't look similar to the we have seen before. Here the main tool is a wheel, and there are no strings, both in this and in these machines. And also the dimension looks much smaller than the actual machine. How is it possible?
Well, the fact that the machine that we have at the museum is bigger than Poleni's original drawings may be connected to the fact that Poleni had made this machine in the mid-18th century for teaching. It was meant for teaching. So that may be the reason why it is bigger. As for the other differences, well, this is still a mystery. Maybe some parts are missing. But also we know that several instruments of the Cabinet of Physics were restored during the 19th century. So this machine may also have been restored at the time and transformed in some way. In any case, there is still a lot to study and to understand in this machine, I would say.
That means that today there are no existing machines like this one designed by Poleni, isn't it?
Well, yes. As far as we know today, it seems there are no such machines.
There's only one way out. We have to reconstruct it, starting from the text.
Poleni's description appeared very detailed. He also included the dimension of many pieces. After understanding how the machines have to work and the role of all their components, we implemented such designs in 3D digital models that allowed us to hypothesize some missing data, like lengths or shapes, to construct them for real. We realized some preliminary prototypes by 3D printing, which gave us tangible feedback. The next step was to find a craftsman to construct them in brass and wood, as in Poleni's design. It was surprisingly quite difficult, because most of the pieces are quite small and they were built with outdated techniques like solder, for instance. Finally, we found our man, Huygens, a 2-day Renaissance craftsman and artist who accepted the challenge of reconstructing Poleni's machine from our technical drawings. His reconstructions are hosted in the Cabinet of Curiosity of the University of Brest, an informal museum and workshop for mathematical and physical instruments. Welcome to the Cabinet of Curiosity. Here is Poleni's machine for the tractrice built by Huygens next to the original drawing. Let's see how it is made. Here is the arm on which a case can slide and which can be fixed at different positions by a very tiny butterfly screw. The case contains a smaller box where the wheel's rotation axis is fixed. The wheel protrudes from the box by a few millimeters, and one can see its tiny teeth that will trace the curve. The rectangular frame shows several holes. One is for fixing the rotation axis of the arm, the others for defining the system of Cartesian coordinates with respect to which the curve is drawn, as we'll see it a bit later. The frame can slide freely between two guides screwed onto the wooden board. They can be loosened to put paper on the board and clamp it. Let's now reassemble it and see how it works. The frame is pulled while the operator presses vertically a finger on the wheel box, and so the wheel traces a tractrice. But doing it this way is not working properly. To improve the grip of the wheel and to see the curve, we need to choose a paper so that the wheel can leave a visible trace, resembling a thin furrow. For the first time in nearly 3 centuries, such a machine is now back in action. We can see clearly that the arm indicates the direction of the tangent to the curve being traced. This direction is given by the wheel, more precisely its rotation plane. The distance between the tracing wheel and the origin on the arm remains constant. It is the constant tangent which defines the tractrice. If we want to study the curve more precisely, we can use carbon paper. Different positionings of the case on the arm give different tractrices, as we can see here. By marking the points through the holes of the frame, we can trace the axis of the Cartesian system of coordinates, the asymptote and its perpendicular intersecting at the origin point. The second machine, like the first one, has an arm which materializes the direction of the tangent to the curve being traced. The curve is traced by the wheel housed in its box. Here the box is fixed at the end of the arm. The wheel is right under the center of the disc on top of the box. The transversal slot is fixed onto the sides of the frame with 2 little butterfly screws. The frame is square with higher longitudinal sides. It has some holes to allow defining the axis of the coordinate system. Here again, the frame slides between 2 guides screwed onto the wooden board. Reassemble it. We see how the transversal slot is fixed on the frame side, and then how the arm slides around the support axis, which is smelted to the frame. When operating the device by pulling the frame while pressing 1 finger on the wheel box, the box is kept in contact with the transversal bar. Thanks to the disc on top of the wheel box, the wheel is kept at a constant distance from the transversal bar. This is our moment of truth. Is our quest for the exponential completed? By using carbon paper, one can study the curves traced by the machine. For each position of the transversal slat on the frame, and for each starting point of the wheel box, we mark the point through the holes of the frame and pull the frame while pressing with one finger on the wheel box to reinforce the weight. Then we can trace the asymptotic axis, and finally we can mark the constant length, the so-called subtangent, which characterizes the traced curve. Suppose that we don't yet know that exponential are curves with constant subtangent. How could we convince ourselves that our curve is actually an exponential? First, remember that the same curve can represent both the logarithmic and the exponential functions. We just have to switch the axis. One could have the idea of testing the curve for the characteristic property of the logarithm of transforming products into sums. The axes of the coordinate system are already drawn. The asymptotic axis is called the y-axis. We place the origin of both axes. Then we say that this point is the unit on the x-axis. When this is done, we can place points with abscissae 2, 3, etc. Now, let's view this curve as representing a function, hopefully a logarithm, as we do it in a more modern way. When we place the origin and unit on the y and x axis, we would say in terms of functions that the image of 1 by the function represented by the curve is 0. We'll say in a shorter way that 0 is the image of 1 by the curve. In the same way, we take the images by the curve of the points with abscissae 2, 3, 3/2, 1/2. The image of 3/2 gives us this length that I materialize by this red rectangle of plastic. The image of 2 similarly gives us this length that we materialize in the same way. When I align the two rectangles along the y-axis, I obtain a length that corresponds to the image of 3 by the curve. We can show that the image of 1/2 is the negative of the image of 2 using a similar consideration. We have shown that our curve verifies the characteristic property of the logarithmic function at 2 points. This is not sufficient to prove that the curve is a logarithm, for we should check everywhere, but one may find it convincing enough. Logarithms and exponentials have a base. Geometrically, the change of the base corresponds to a different length of the constant subtangent. For the Neperian logarithm and natural exponential, the base is e, Euler's constant. This constant is usually introduced as a limit, but here Poleni's machine provides us with a geometrical construction of e, Once the subtangent and the trace are given, it is a ratio of two lengths. Given the subtangent, by fixing the transversal slat, and the starting point by making the wheel box touch the transversal slat at a certain height, the machine draws a unique curve. Whatever the subtangent and the base are, we can construct Euler's constant in that way.
Our journey began with a question about how to construct the exponential in a material way. Even though geometrical instruments lost their importance in modern mathematics, they played a foundational role for scholars like Descartes and Leibniz. Geometrical machines legitimized the existence of the object introduced by formulas. We suggest that such an instrumental perspective is useful even today to perceive the tangibility of math. In the case of the exponential, that can provide some concrete insights that are not evident in the various usual definitions. This approach can hopefully be applied to create meaningful didactical activities, as we try to do.